Welcome to the AI Research Roundup. I'm Alex. Today we are looking at a paper from the Hugging Face trending list, published on December 15th, 2025, just yesterday. It shows that by reshaping how visual tokenizers are pre-trained, you can get about a 66% FID improvement in generation and roughly 4.1 times faster convergence, simply by reallocating compute to smarter pre-training. The paper is titled, Towards Scalable Pre-Training of Visual Tokenizers for Generation. And, as we will see later, the implications for large-scale generative model training are quite significant. Also, the author shared a GitHub repo where you get the full VTP implementation, ready-to-use PyTorch models, and a quick start script to run it as an autoencoder, clip-style model, or SSL feature extractor. There are evaluation scripts for zero-shot, linear probing, reconstruction, plus generation experiments plugged into Lightning DIT. On Hugging Face, you'll find VTP small 0.28 billion, base 0.38 billion, and large 0.78 billion visual tokenizers, plus code examples for autoencoding, clip-style retrieval, and SSL features. Figure 1 summarizes the core idea that smarter tokenizer pre-training alone can make downstream generation much better. The top panel shows the visual tokenizer trained jointly with reconstruction, self-supervised learning, and clip-style image text contrastive loss, so the latent codes capture semantics instead of just pixels. The middle panel sketches how these latents feed into a standard diffusion generator without changing its settings. The bottom graph plots generative FID versus training compute and shows that scaled tokenizer pre-training steadily improves generation, while a plain autoencoder plateaus early. Figure 2 shows that better semantic understanding directly tracks better image generation quality. The horizontal axis is linear probe accuracy, which roughly measures how well a simple classifier can read concepts from the latent codes. The vertical axis is generative FID in reversed form, where higher values mean better generations. The gray autoencoder points cluster with low understanding and low generative quality, so they stagnate together. The green versus TP points form a rising line, meaning that as understanding improves, generative quality improves in lockstep. Figure 3 spells out how the versus TP tokenizer actually learns, and then plugs into a diffusion generator. The top pipeline shows visual tokenizer pre-training, where a single vision transformer feeds 3 heads for contrastive learning with text, pixel reconstruction, and self-supervised learning with a teacher model, so the latent codes become both semantic and faithful to the image. The bottom pipeline shows diffusion training and sampling, where noisy latents pass through a diffusion transformer and a pixel decoder to produce final images. The key message is that all 3 pre-training objectives shape the same latent space that the diffusion model later uses for generation. Table 1 shows that a vision transformer-based autoencoder can match or beat a convolutional one for the same tokenizer role. The columns report compute cost, number of parameters, reconstruction PSNR, which measures pixel fidelity, and generative FID, where lower means better samples. The mid-sized vision transformer already slightly improves both metrics over the convolutional baseline at far lower compute. The large vision transformer achieves the best generative FID while keeping reconstruction quality strong, so transformers are a solid backbone choice here. Figure 7 makes the scaling story concrete, showing that the versus TP tokenizer keeps improving generation quality as data and model size grow, while a plain autoencoder largely stalls. The left panel plots generative FID versus pre-training data size and shows versus TP improving steadily as data increases. The middle panel shows that larger versus TP encoders benefit much more from extra training compute than autoencoder encoders. The right panel compares different decoder capacities, and again, versus TP gains strongly with compute, so scalable tokenizer pre-training reliably translates into better downstream diffusion generation. So the big message is that making visual tokenizers understand images through contrastive and self-supervised learning plus reconstruction fixes the pre-training scaling problem and directly boosts generative quality. This opens a path where we pour compute into tokenizers, not just bigger generators. That is it for this episode of the AI Research Roundup. I am Alex. Thanks for listening.